Hi class, welcome back to Electromagnetics. So we want to wrap up part 6 of the course today and extend our discussion on transmission lines in this distributed circuit model to go from the parallel plate model that we had just to any arbitrary cross section. So we'll look at that today. First, we want to take a look at a historical background, again, of a person who contributed to electromagnetics and that field. So this individual was self-taught. He was a self-taught electrical engineer. To our knowledge, he had no formal education other than high school, and from that he was able to do just tremendous things with it. With his work, he started working with his uncle, who was Uncle Wheatstone, in telegraphy, doing the telegraph. And hopefully Wheatstone is a familiar name to you. You've probably studied in one of your circuits classes the Wheatstone Bridge, and this is the same person, so it was his uncle. Then he continued to work for other electrical engineering companies or for other companies as an electrical engineer. We do have a photograph of this person because he is rather contemporary. Maybe you recognize him. This gentleman's name is Oliver Heavyside. Lived from 1850 to 1925. So some of the notable things for Mr. Heavyside. He revised Maxwell's equations. Originally, Maxwell's equations was made up of 20 equations with 20 unknowns, and so it was rather laborious to work through that. And so Heavyside took it upon himself to modify that and develop the notation to simplify that into a much more compact form, which makes it a lot easier to understand or think about what's going on. So he's the one that ended up applying the curl and divergence notation to Maxwell's equations. He invented and applied the Heavyside step function, of course, named after him. So those of you that have had communication theory or signals and systems, you probably learned about the Heavyside step function, and it is used in communication circuit analysis quite a bit, and he developed that. He did develop transmission line theory and application of Laplace, so that when, again, in circuits and signals, if you've worked with the Laplace transform, he was able to make those connections and some of the transmission line theory that we're talking about in this course even. And then finally, he predicted the existence of the ionosphere. It wasn't confirmed till after his death, but he predicted it. Of course, the ionosphere is the part of the atmosphere that has the layer of charged particles, and is actually this layer in the atmosphere that enables antennas to work over long distances and kind of bounces the waves. And so he was able to predict that. Some interesting stuff about Heavyside, and actually kind of sad. Toward the end of his brilliant life, he developed some very odd tendencies that led many to believe that he was having some mental issues, such as he started signing his name on all documents with the acronym WORM, worm. It's capital WORM. And to this day, nobody knows what that stood for. He never told anyone. He just one day started changing the way he signed things, and then that was it. And as far as we know, he never told anyone or wrote down what that was for. He started painting his fingernails pink, which is kind of odd. And again, no explanation, just from some certain point on, he always had pink fingernails. And then finally, the one I thought was probably most bizarre is in his house, he took all the furniture out and replaced all the furniture with large blocks of granite. So when you go in his house, you'd have to sit on a big block of granite, and you'd have a bigger block of granite for a table. Yeah, maybe that was a design choice. I don't know, but it does seem rather odd. So again, we're wrapping up part 6, looking at transmission lines and arbitrary cross sections. We went to parallel plate to set up our math and kind of made things easy for us, but now we want to extend this to any type of transmission line. So again, in this chapter, we've examined Maxwell's equations to electromagnetic fields for static fields, quasi-static fields, and higher frequency fields. So we want to wrap it up now by applying the transmission line approach, which is a distributed circuit approach to structures that have any arbitrary cross-section. And that is structures other than the special case we looked at last time, which is the parallel plate transit lines. So in previous analysis, we strategically arranged the situation such that our electric and magnetic fields are simplified, such that they only had z components, then that z direction and time components. So those are the only two things that affected our fields. Well, now we need to look at the arbitrary case, and so we need to take into account that it could have components in any of the three directions in time, and also it could be each component could be affected by those, and then you'll have an x and a y component, even though it still be transverse to the z direction. We could tilt that axis and make it to where it does have an a and a y, x and a y contribution. Same thing with the magnetic field. So there won't be a z component because we are going to keep the condition that it's transverse. But other than that, and so that being the case, since there is no z component, then we can still consider these as TEM waves as we did before. So let's think about this then for an arbitrary arrangement. And so we have, instead of two parallel plates, we can bend the plates around until we connect them on the ends like this. So this would be one plate bent back on itself. This would be the other plate bent back on itself, okay? And so these are plates made of conductors. And so we know from the boundary conditions that the E fields, any E fields that come in contact with this conductor plate have to be perpendicular. So we can go ahead and start drawing our E field lines perpendicular all the way around. Well, we know from Maxwell's equations then, if we have a magnetic field that's associated with this, it has to be perpendicular to the electric field lines. So we can draw this circular line all the way around, and every time we come in contact with one of these E field lines, we again have to make it perpendicular. And so then from there, we can continue to extend our E lines out and then draw more of our magnetic field lines, again keeping them all perpendicular all the way around until we completely fill the space in between the two conductors. And so this is the premise that we'll build on moving forward, and we'll see the result of that is we're creating these what we call curvilinear squares. And so they're squares in the sense that they have four sides, but we call them curvilinear because the sides aren't perfectly straight. They do have some curve to them. But we can work with that, and we'll see how as we move forward. So for our analysis, we're going to put some definition to some things here. We need to keep this in mind as we move forward. So in this case, we only divided it up with one magnetic field line here. This is one conducting plate and the other conducting plate. And so you'll see that all of the curvilinear squares inside that plate are going to have the A designation. And so we did eight of them. 1, 2, 3, 4, 5, 6, 7, 8. So 8A, 1A, 2A, 3A. And then in this external path here around there, these will all be designated as B. And so we'll again have 1B, 2B, 3B, 4B. And so you can see these are the E lines, and so they should also be in association with our current density for conduction lines. If there is any conduction in this dielectric, we're assuming this is some type of dielectric here. And so if there is any current, it'll be flowing from the inner plate to the outer plate. And of course, we can see here that we'll have the directions here along the outside. It's coming out of the screen, and then on the inside here, the X's designates going into the screen. And so we'll have at the edges the voltage equal to 0, and on the inside conducting circuit surface, or somehow we're applying a voltage V equals to just arbitrarily say V. So I think we have everything defined here. So with these definitions, of course, Z is going in and out of the board, X is up, and Y is to the right. So let's move forward and see if we can't put some mathematical definition to what we see here. So using this model for this arbitrary cross-section, the newly defined sections, we can now calculate the inductance per unit length as follows. So we know that the inductance is defined as the flux over the current. Well, in this case, we'll have flux associated with that inner curvilinear circle sub A, phi sub A, and then the outside will have flux as well, so it's phi sub B. And then we'll have currents flowing through each section. Remember, we sliced it up into 8 sections, so it has, whatever goes through A also goes through B. So it's just I1, which is I1A and B. I2, it's the same current that goes through them. So if we look at that, we can rearrange this a little bit to say that we can say that just as 1 over phi A, 2 over phi A, so on and so forth, plus 1 over phi B, 2 over phi B, so on and so forth. So this is just a mathematical transformation here, nothing fancy, but there's a reason for it, because now we can see that we have the per unit inductance of each of the curvilinear squares. So there was the 1A, the 2A, so on and so forth. And so if we can draw this to where these are symmetrical and fairly simple, then we can make this work out pretty easy. Using the same approach, we can take a look at the capacitance per unit length. So remember that the capacitance is the charge over the voltage. So here we'll again have a charge associated with each of the 8 slices, and then we'll have a voltage drop across the inner circle and then the outer circle, VA and VB. Well, likewise, we can do some math tricks with this as well, and it's basically just algebra, and we come up with 1 over VA over Q1, VB over Q1, so on and so forth, to where we can substitute these back in to use the capacitance per unit length of each of the squares here. And that's how that would work out. And then finally, as you can guess, we're going to do the same thing with conductance. Remember, conductance is the conducting current divided by the voltage. So here we've got the current 1, 2, 3. Again, if it goes through any part of 1A, same current will go through 1B. So it's just 1, 2, 3, 4. And again, the voltages are associated with the voltage drop across A and across B. So again, as we did with the capacitance, we kind of do that little algebraic trick there and flip it around, and now we see that we've got the per unit conductance of each little square. So using this, we can now extend this indefinitely for arbitrary shapes of M segments in the angular direction and N segments in the radial direction. Okay, so again, M is the segments in the angular direction, and so how many angles do you have all the way around? So if it's 60 angles, 60 angular slices evenly done, that's what M would be, and N is the segments of the radial direction, so how many cuts. So here we just had A and B, but we can do C, D, and E. So with that in mind, then we can rewrite those previous equations in these compact forms, this compact notation. So it's just the sum of the 1 over each curvilinear square, inverted and summed up for each of the N sections. So this is a compact way, and we'll see how we use this in just a second. So if the maps are made up of curvilinear squares, then the ijth components of the inductance, capacitance, and conductance terms simply become mu, epsilon, and sigma, or the permittivity, permeability, and the conductivity respectively. So this means that the effective per unit values are then simply the properties of the material that's in the dielectric times this ratio of the number of angular cuts by the number of segments. And so, we can draw our squares out however we want, as fine as we want, or as coarse as we want. As long as we can calculate this accurately, then we can just multiply that times our mu, epsilon, and sigma. And so what this is telling us then is, these number of squares we have, the per unit lengths, these squares are going to be little small circuits themselves that are either in parallel or in series. And so this takes into account that ratio to give us the new per unit values. So let's look at an example. So we have this coaxial cable, and so we take this coaxial cable, and of course we have a conductor in the middle, and then we have this dielectric. If you've ever pulled back dealt with the coax and pulled back, you know there's the big white plastic in the middle usually, and then there's the sheath on the outside, which is a conducting surface as well. So this is a transmission line, and so in the radial direction we've got 2 pi over n. So you know it's 2 pi all the way around. So how many slices we make, it's m slices, so it's 2 pi over m. So the side of the curvilinear square at any radius then, so the sides here would just be r, the distance we are out, times 2 pi over m. And again, this is just basic geometry. So that being the case, the total number of squares in the radial direction then is given as the integral from r equal to a to b, so from a here to b, which is the outside radius, m over 2 pi, so we know how many cuts we've got all the way around, dr over r. Okay, so when we integrate that and plug all the values in, we come up with the result of m over 2 pi natural log of b over a. This is true for any coaxial cable. So with these expressions for m and n, we can now develop expressions for our per unit components as follows. Our per unit inductance is the permeability of our dielectric over 2 pi and natural log of b over a. So you know we can vary this b and a to get whatever value we want here. Same thing with the capacitance. It just gives us an equation in terms of the property of the material. That's this dielectric in here, so the permittivity, and then it's natural log of b over a, and likewise the conductivity. This conductivity is a physical property of whatever material is in here, b over a. So here we can see that we can vary all 3 of these by varying the a and the b values, which in a sense just makes the thickness of this dielectric in between here larger or smaller. So the same procedure can be done to other common structures like these and their per unit values. So here you see there's the parallel plates that we have that has a certain width and a certain depth, and this is assuming that the depth is much, much less than the width. We have our coaxial cable. We can have 2 cables that are separated by a distance 2d, and then we can have these off-center cables, or we can have this coax that has actually 2 conductors inside of it, like this. So remember the A, B, C, D, and E as we look at the next sheet. So in this next sheet, you can see we again have our A, B, C, D, and E. These correspond to the shapes we saw on the last page, and they've worked out for you how you can calculate these per unit length values for each of these scenarios if you know the physical dimensions. In most cases, it's like an A and a B, or a depth and a width, or you can have multiple dimensions that are defined on the graphs on the previous page. So these are pretty handy. These are pretty common shapes, but again, you can do this for any configuration you want, and you can get as complicated or as simple as you want. And we'll have some homework problems that are associated with this.